Ladies and gentlemen, welcome to this event. Welcome to the historic Aula building of the University of Göttingen. My name is Ben Buring and I have the pleasure to guide you through tonight's event. Today we will be unveiling a plaque. Göttingen is deemed Historic Site of Physics by the European Physical Society. We will do this here in this building and not at the site where this plaque eventually will end up, where it will be displayed. That is in the Bürgerstraße in front of the Forum Wissen for everybody to see. But there's many reasons why we do this today here. One of them being that we all wanted you to attend, and the fact that this is next to a quite busy street and traffic is very loud, and we could not have heard this wonderful music. And in addition, you will hear a lot of names tonight, a lot of brilliant scientists' names, and they have most likely all one thing in common. And that fact is the point that at one time in their career, in their life, they've all been in this building. They've all attended an event in this building eventually, because they all worked here in Göttingen. So it's quite fitting to be in that room. We will start with the official welcome, and I'm happy to announce now the President of the University, Axel Schölmerich, and the Mayor of Göttingen, Petra Broistedt.
Yes, welcome you all. This is my 4th week in this position and the first time I'm allowed to speak from here. So I thank you all that you made this possible. First of all, I want to thank Julia Barta and Dr. Antonius Adamske for this beautiful introduction. That was Jupiter. We'll hear more about some other planet in the program. Dear Professor Schachtner, Secretary of State for the Ministry of Science and Culture in the state of Lower Saxony, dear Mayor Broistedt, dear members of the Landtag of Lower Saxony, Carina Herrmann, Marie Kollenroth und Michael Lühmann, dear Dr. Andretta, former President of the Landtag of the state of Lower Saxony, dear members of the City Council of Göttingen, dear Professor Sakellariadou, President of the European Physical Society, dear Professor Richter, President of the German Physical Society, and dear Professor Köster, Dean of the Faculty of Physics. Dear speakers of tonight's evening, Professor Schirmacher, Professor Blümer, and Professor Hollig, honored guests and colleagues, and it is really a pleasure to welcome you here to this event of being declared an EPS site of physics, to the city of Göttingen. And as you've already heard and probably already know, this is a place where many great achievements in physics happened. And here, that's why this city welcomes you all for this occasion. We've also made sure you have the proper weather, so also enjoy the beautiful city of Göttingen with these historic buildings. Take time to take a little tour and enjoy the whole city. We have the United Nations Year of Quantum Physics, and the contributions that led to the description of quantum mechanics, its foundation, principles, and mode of operation are unique insights into the physical reality of our world, which still characterize and also challenge our view of this world today. I won't go into the historic details because there are more competent speakers in the program that will make sure that all aspects are being explained. The joy in the city about the fact that we're being honored as a research location, a tradition that stretches from Lichtenberg to the present day. It extends far beyond the university, and really this is the Göttingen spirit which is active here, and you may be able to feel that a little bit. Our thank not only goes to the scientists who developed these theories, but also to the many people who have contributed significantly as technicians or employees at those times. There's a special exhibition in the Forum Wissen, which is called in German Was zum Quant, and in English that sounds what the quant, and I'm kind of scared to use that in the English form because of the association that may be in your heads right now. The university hosts a central lecture series which starts at the end of the month, 100 years of quantum mechanics, Göttingen's contribution to a scientific revolution. And there's about 110 events on the German Physical Society's website to mark the quantum year, and alone 29 of those are happening in Göttingen. I also appreciate the contribution of Professor Arnulf Quat as the local organizer of the ongoing spring conference of the DPG, and I look forward to the autumn conference in September with local organizers Professor Weitz and Professor Kerein. Physics research has not only been an important pillar of research at the University of Göttingen in the past, it's also at the center of our scientific research of this day. It remains a very important field with outstanding research achievements by excellent scientists, numerous collaborative projects, and also very significant results of individual research. Just last week, Jens Frahm received the Bundesverdienstkreuz for his revolutionary contribution to the development of MRI technology. Professor Annette Sibelius has made fundamental conceptual methodological contributions to the statistical physics of condensed matter, and Professor Stefan Hell, a physicist who received the Nobel Prize for Chemistry in 2013. He has continuously developed his discoveries and achieved unprecedented levels of detail in microscopy. Important building blocks for our cluster of excellence, multi-scale bioimaging, which is at the University of Göttingen, and we're all looking forward to the next phase of funding starting next year. Research is change and progress and dynamic change. Newly appointed colleagues in recent years are the promise for scientific progress of the future. We at in Göttingen take special care to offer the best possible environment for the development of young careers, and I'm looking forward to see that efforts result in further significant contributions. And with that, I welcome you again, and I'm very happy that you all made it to Göttingen, and I wish you a good time here and insightful talks in this event. Thank you very much.
Good evening, ladies and gentlemen, dear guests. I would like to extend a very warm welcome to you and our distinguished guest. First of all, my favorite State Secretary, Professor Schachtner, dear Joachim, Professor Richter, President of the DPG, Professor Schölmerich, our new President of the University of Göttingen, Vice President Brümmer, and respected members of the University of Göttingen, respected members of the State Parliament of Lower Saxony, Carina Herrmann, Carola Margraf, Michael Lühmann, former President of the State Parliament of Lower Saxony, Dr. Andretta, dear Gabi, esteemed members of the Göttingen City Council, Professor Sakellariadou, President of the European Physical Society, Professor Richter, President of the German Physical Society, Professor Köster, Dean of the Faculty of Physics, and all other honored attendees. It's my great pleasure to welcome you all to Göttingen. Today, we celebrate the special role our city and the university have played in the history of physics. Over the centuries, many scientific disciplines have shaped Göttingen, but physics has certainly left one of the deepest marks. How has this relatively small city been able to attract so many brilliant researchers? One reason was the university's layout as a center for mathematics and physics. But the city itself has played its role too. An inspiring place where people work together in a culture of trust. I picture brilliant scientists making the most of Göttingen's short distances, exchanging ideas and building networks long before the internet. It is what the people call the Göttingen spirit. This close, trusting collaboration has resulted in an impressive number of Nobel Prizes. More than 40 Nobel laureates have ties to our university and our city. The Göttingen spirit is certainly not a thing of the past. Göttingen remains a center of top-tier research, from the university to our four Max Planck institutes and many more well-renowned institutions. Only 10 years ago, the Göttingen-based physicist Professor Hell won the latest Nobel Prize for our city. As mayor of the city of Göttingen, I'm honored to receive the recognition as an EPS Historic Site today. The timing couldn't be better. It has been 100 years since Max Born, Werner Heisenberg, and Pascal Jordan laid the foundations of quantum mechanics here in Göttingen. I'm looking forward to your contribution later on, Professor Schölmerich. I'm sure we will learn some fascinating new facts about this anniversary. I want to thank the European Physical Society. On behalf of the city of Göttingen, we are really proud to be awarded by you. Thank you so much. And just as a side note, we will continue to celebrate our scientific legacy. In 2027, we will mark another major anniversary, the 250th birthday of Carl Friedrich Klaus, and you are more than welcome to celebrate with us. As we celebrate past achievements, we must not ignore today's challenges. Science is under pressure. In many places, scientific work is currently being censored. Funding is being cut. Skepticism towards science is growing. Many people, also extremely right-wing politicians, believe more in so-called alternative facts than in scientific researches. Entire fields, climate research, gender studies, even health research are being undermined. History showed what happens when science is restricted. Just years after Göttingen's golden age, fascism chased away its scientists and ended an era of excellence. Ladies and gentlemen, let us not take academic freedom for granted. As a society, we have to make sure that research remains unhindered and free. Creating knowledge is a fundamental part of our city's identity and growth. It's up to us to keep this success story alive. Thank you.
Though a foundation by statute, the University of Göttingen is a public university, a public institution, and the importance of public institutions of education and learning and research were just pointed out. And then that is why we are very happy to have Professor Joachim Schachtner here with us today, Secretary of State for the Ministry of Culture and Science at for the state of Lower Saxony. Please, the floor is yours.
Yes, thanks a lot. Science and culture.
Science and culture, that is true. I'm so sorry. That's very important here.
I had to say that. Okay. First of all, I want to welcome all of you here in this wonderful academia hall. of the University of Göttingen, and that this hall has a wonderful history. So part of that we are celebrating actually today. So, magnificence, dear President of the University of Göttingen, dear Axel Schölmerich, dear Mayor, Petra Broistedt, dear members of the Landtag of Lower Saxony, here sitting in the second row, wonderful that you're all here. I also want to welcome Gabi Andretta, the former president of the Landtag of the state of Lower Saxony, dear member of the City Council of Göttingen, and now comes the spelling of the name, dear Professor Sakellariadou. Nearly perfect. Thanks for this tip to talk this slowly. Right. So you are the president of the European Physical Society. It's an honor that you're here. Dear Professor Richter, president of the German Physical Society. Dear Professor Köster, dean of the Faculty of Physics here at the University of Göttingen. So again, welcome, dear all. It's both a great honor and a true pleasure, so to speak, to be here today and to pay tribute to Göttingen as a historic site of physics. This is not only because it reminds us of the golden moments of science, nor merely because it underscores how groundbreaking physical and mathematical theories have transformed the world and continue to shape our present. The latter, of course, is central. It is also a reminder of the fragility of free science, for in the 1920s, anti-rationalism, anti-democratic, nationalist and anti-Semitic ideologies threatened scientific freedom. In 1925, Max Born, Werner Heisenberg and Pascual Jordan laid the foundations of quantum mechanics here in Göttingen. 8 years later, their paths diverged. Born was dismissed as one of 45 faculty members at the University of Göttingen under the law for the restoration of the professional civil service and forced into exile. A similar fate befell Eugene Wigner, John von Neumann, Wolfgang Pauli, Viktor Weisskopf, just to name a few. They all left Germany, leaving irreplaceable gaps behind. How I wish I could say all of this is history and lessons have been learned. Yet right now, the freedom of science is being questioned in many parts of the world. Just last week, the Lower Saxonian Parliament debated this very issue. The frequently cited Academic Freedom Index 2025 shows that when anti-pluralistic parties gain influence, it is often accompanied by a decline in scientific freedom in the respective country. Even in Germany, the index shows a decline in scientific freedom. This, ladies and gentlemen, should deeply concern us. This makes it even more important to remember the year 1925. It is valuable to shed light on how it was possible between the world wars for a theory to emerge in Göttingen that fundamentally changed our understanding of nature. We look at well-known and unjustly forgotten scientists whose spirit of inquiry united them. Researchers who pushed forward, venturing into previously unknown realms. They came from Europe, the United States, and were both Jewish and Christian. They garnered international support, such as from the Rockefeller family for the Mathematical Institute. From here, connections were made to research institutions worldwide, making this historic site of physics also a story of internationalization. We see how women scientists entered the stage, and at the same time the resistance they faced, such as that experienced by Emmy Noether, Maria Göppert-Meyer, and Lucy Mensing, moral and philosophical questions arise about a science that, through quantum mechanics, paved the way for the atomic bomb. We reflect on the roles played by Werner Heisenberg and Robert Oppenheimer. Thus we find ourselves confronting research for war, still not just a historical matter. More on these aspects and others can be explored, and it was already mentioned, in the remarkable special exhibition at the Forum Wissen. Dear guests, the historic site of physics leads us to questions of the present and to current research in Göttingen's scientific community. At the Faculty of Physics, not only is the groundbreaking research of 100 years ago remembered, but it also continuously advanced with new ideas. The recognition by the European Physical Society, especially in the International Year of Quantum Science and Quantum Technology, makes the Göttingen institutions and their achievements even more visible. This also highlights the efforts across Lower Saxony, the Quantum Valley Lower Saxony, based in Hanover, brings together research on quantum technologies from both universities and non-university research institutions. I think this very nicely represents the high importance of this field of research in Lower Saxony. For this field to be a fruit, a strong, free, and innovative scientific landscape is essential. We need cooperation instead of confrontation, international collaboration, open doors, and, very importantly, mutual respect. Only then can a place become an inspiring one, where great things are possible, just like in Göttingen in 1925. 100 years later, this serves as a call to us all to create such places and protect them from those who feel threatened by free, critical science. So thank you for your attention.
The title EPS Historic Site is given to the city of Göttingen by, we heard it already, the European Physical Society. The suggestions for that status and this title are traditionally forwarded and supported by the member institutions of the European Physical Society, in our case, the German Physical Society, DPG. The initiative for this application grew root in the Faculty of Physics of the university. Therefore, I'm very happy to welcome the three heads of these three institutions, and I would like you to join me here on stage, Professor Sakellariadou, Professor Richter, and Professor Köster. Now, Professor Sakellariadou, the EPS hands out, you have a microphone, there it is, wonderful, gives these titles, the series EPS Historic Site. Why do you do that? Where does that come from?
Well, first of all, it's an enormous pleasure and honor for me as a physicist to be here. There's an endless list of mathematicians and physicists who worked in this city, so for me it's a tremendous pleasure and honor. So the European Physical Society, as you know, is a federation of all national physical societies in Europe, and the EPS Historic Sites is something that has initiated in 2011 by Professor Luisa Cifarelli, who at the time was the president of the European Physical Society. And the idea behind that is to commemorate places mainly in Europe, but not only Europe, which are very important for research, for development, for history in physics. So there are up to, right now, 76 historic sites in 26 countries. In a little while, there will be 77, And the city of Göttingen would be the 77th historic site of EPS and the 10th one in Germany. So we would like really to acknowledge the tremendous work, the tremendous number of people who worked here and they made this huge development on a theoretical point of view, but as well on technologies.
Thank you very much. Professor Richter, the DPG supported and forwarded this application. Why did you do so?
Oh, yes. Well, concerning the history of quantum science, I think we cannot think of a more appropriate place than Göttingen for that. And if you think of, the tremendous impact quantum physics has on society these days globally, you should make clear, everything started here in Göttingen, really. And this was 100 years ago. And as we heard already, 1925, the first, fundamental works and fundamental of quantum mechanics was worked out here. And this, I think, in a bang, within very few months, Heisenberg and Born and Jordan had their papers. And, well, as DPG, I should mention, we are rather proud that young Heisenberg, at that time, at the age of 23, he was already a DPG member. So you see that being a DPG member you might get famous afterwards. Yes. Anyhow, but what is way more important, besides those three, this makes Göttingen. There were many more mathematicians and physicists afterwards and at the same time that really shaped quantum physics here and then for the world. And I think that's why the university and why Göttingen is so important. That Göttingen somehow provided the perfect environment indeed for these brilliant minds to get together, to meet here in the streets and to communicate and to build this unique community, to build thereby something great.
Thank you. Professor Köster, now you're representing the university, today's researchers. Why is an award like that for the city important for the university and for you?
Yes, I think the award, which we're very happy about, so thank you very much for deciding such and for coming here. It recognizes Göttingen as a place for science, and I think it also recognizes the collaborative spirit that we still have today. It's a place for science for the university. We've heard a lot about this today, but there's also a lot of non-university institutions here, and we work very closely together. And another thing that happened at the time, and you just mentioned it, is this very strong collaboration between physics and mathematics. And I think we still have this today. So I think this is also an award that reminds us today, the scientists today, that we should all work hard, we should work together, and there's still a lot to do and still a lot to discover.
Thank you. Me being an historian, I always find quantum physics and quantum mechanics very abstract, very hard to tackle, but then you always get a little glimpse with every conversation you have, and that's why I also wanted to ask for the non-physicists in the audience. Now, you as expert in physics, what is your favorite part, quality, fact about quantum physics that maybe not everybody knows? Maybe the president starts.
Well, I will take a specific one, which has to do with Göttingen. I think it is maybe not so known. And this is about the deep and not yet understood relation between quantum physics and number theory. And more precisely, starting with David Hilbert. Hilbert showed that if you have, now it gets a bit physical, technical, Hilbert, famous mathematician, showed that if you find a quantum system with a spectrum, with the eigenenergies that coincide with the zeros of Riemann's zeta function, then you would have proven the Riemann conjecture. And the conjecture by Riemann was set up in 1859 here in Göttingen. So you see, suppose this could be proven, then Riemann is the first quantum scientist, in a sense.
Very good, very good. What's your favorite part?
Well, for me there are two important things. One is a purely theoretical one, which is basically, as you know, at the time, there was, as you mentioned, a very big kind of affinity between mathematics and physics. So on the one hand, we had quantum mechanics. On the other hand, we had relativity, which culminated in general relativity. So we know that there are very deep connections between the two, that they led to very important deep questions and some kind of debates between Bohr and Einstein. And still, to find the theory that is going to reconcile quantum mechanics and relativity and gravity is an open question. We have a proposal. We don't know which is the correct one, if any of this. That would be the theory that we call quantum gravity. And the day that we will have it, and that started from the time of Einstein searching for that, we'll be able to unravel the mysteries of the beginning of the universe, which we don't have. So for me, this is the one. And the second is a purely technological one, which is lasers. Because I'm very much involved with LIGO, which is the Laser Interferometer Gravitational Observatory. We would not be able to find direct detection, which we did, of gravitational waves. And now we have about a few hundreds of events without having a laser. We produce the laser, we're able to magnify that in 200 watts of power. We are able then to stabilize it about 100 million times than what it is original. We split it along the arms of our detector. We send it back and forth about 300 times, and we're able to find the distortion of space-time smaller than the thickness of a human hair. This, to me, is an amazing accomplishment. We could never be able to do it without lasers or without quantum mechanics.
Thank you very much.
Yes, I have a hard time deciding because there's so many really amazing discoveries. So I will pick something that's indirectly related, and that is that at that time, and that was between the two wars, people really started to collaborate internationally. People from other countries came to Göttingen. When you think about it, that's really amazing. And it was also, as far as I understand, kind of the time when the postdoc phase, as we know it today, was invented. So people sent their students to other places for a year or two, and then they came back. And so they really collaborated internationally. And I think this is something that, we can still very much benefit from today, and we should also not forget that is very important.
Yes, thank you very much. Last question for you all. Now, we're talking about history, and you already made the connection to what's the next big thing. I've hesitated, I won't ask you when we find that, but it's going to be soon, I guess.
We have to come here, all of us. If we're here, we work all together, mathematicians, yes, physicists, that's the only way we can do it. So it's an open invitation.
You have to talk to the president about these
I will.
and maybe to the one sitting next to him. And, let's extend the physics with it. So how do you, let's phrase it differently. Of the many things that quantum mechanics, quantum physics makes possible or made possible, what is the most important thing in today's world, how that physics, quantum physics and quantum mechanics shaped the world today? What is the most important thing for you? Short answer. Mr. Richter.
Well, I would say, looking into the future, but from now, the most important thing, I think, is renewable energies. Mm-hmm. So we call climate crisis the biggest crisis, so we need to fight climate change. And this is only possible with renewable energies. So one has to do a transformation in energy supply. And renewables means quantum physics. And there are photovoltaics, which is a prime example. Photovoltaics is not only Einstein 1905, the photo effect. These days, solar panels are, of course, include a lot of quantum technology and facets of quantum physics.
Thank you, sir.
I can only come up with the second important, of course. I would say biomedical imaging, because that's very important for health research, and it's also has the foundations in quantum mechanics.
Yes.
I cannot come up with a third one. I fully agree. First and then second. And then, from a theoretical point of view, I'm a theorist. What I found fantastic is the quantum entanglement, which we know that was done, is the Nobel Prize of 2022. That was a spectacular kind of result that came after a paradox, a debate between Bohr and Einstein. But if you allow me one more minute,
Oh yes, I do.
I would like to say that today, the 1st of April of 2025, the European Physical Society, together with 12 national physical societies, we put forward a statement about quantum physics. We should never forget that Europe was ahead of everyone at the beginning, about 100 of years ago. Europe should remain ahead of everyone about that. Now there is a very big race all around the world because of the technological and, of course, financial implications of quantum technologies. We have to take the example of what happened 100 of years back. People collaborate. We have to do the same. And we also put forward a statement about diversity and academic freedom that we support, and I'm sure that all of us here will support. So this is what I would like to say on behalf of all my colleagues at the European Physical Society, and thank you all for the help. Actually, the German Physical Society was one of the first driven the whole thing about this statement, and we thank you very much for that.
Thank you very much. Now, without further ado, I would ask Mayor Broistedt to join us on stage, and Professor Schachtner and Professor Schölmerich as well. So we shall do the unveiling. As the award is given to the city, as it is for Broistedt's honor and duty to do the unveiling. Maybe the others stand behind it or next to it, because we also need to take a picture, and I will get out of the picture. Let's wait for the photographer. Is that right, Peter? Do we need to arrange something? That's all right. Good. So now, please unveil the plaque. Wonderful. Thank you. Klaus. Thank you very much. It will remain here and it will be put in front of the Forum Wissen for everybody to read and see next to the pedestrian way there. If you get close to it today or later on, there's a QR code on it that leads to a website that is the history wall of quantum physics. Very, very interesting place to develop and to look into all the details of quantum mechanics and quantum physics history, which started much earlier and still goes on. Now we have two short talks and then a keynote. And for these short talks, I will first welcome Professor Johannes Blümer, who will talk about Heisenberg, and then Professor Wolfgang Hollig, who will talk about the MPE for physics during its time in Göttingen. I also wanted to shortly introduce you, Professor Blümer, if I still, I think I still do that, right? So this is Professor Blümer. Welcome. Professor Blümer received his doctorate in physics at the University of Dortmund, and in addition to research stays at CERN, he worked as a research assistant at the University of Mainz, where he habilitated in 1995. After further research stays at the University of Karlsruhe and at CERN, Johannes Blümer was appointed professor and director of the Institute of Nuclear Physics at today's KIT in 1999. From 2015 until his retirement in 2022, he was division head of physics and mathematics at KIT, and Johannes Blümer is also the chairman of the Heisenberg Society, and that since 2022. Now, officially welcome.
Thank you for insisting on the kind introduction. Ladies and gentlemen, inside and possibly, I'm not sure about transmission, but inside and outside this splendid hall, to save some time of my 10 minutes, I will greet everybody from the bottom of my heart, all protocols observed. As was said, there are 76 historic sites until yesterday. Only one of them is actually named City of, and this is Jena. So Göttingen is now the newest entry in this list, and rightfully so. May I quote you, Mayor of Göttingen, Petra Broistedt, from your welcome address yesterday when you invited us to explore the city. Mind your steps, you are walking on historic grounds. I'm grateful and feeling honored talking to you as a representative of the Heisenberg Society. We are a non-profit organization funded in 2012 by people who had personal connections to Werner Heisenberg in 3 categories. Actually, science, music, and marriage. We strive to make Heisenberg's written archive accessible in the open Calliope database, and when you try to explore it, out of the 50,000 digital objects representing 300,000 paper pages, you find 6,000 times the tag Göttingen. We also organize discussion events, and very importantly, we help to bring modern physics to schools. Unsurprisingly, I will talk about some aspects of Werner Heisenberg in relation to Göttingen. Well, his first visit is said to be in 1922 because he wanted to meet Bohr and Einstein. At the time, young Werner was a doctoral student of Arnold Sommerfeld in Munich, and his doctoral examination took place in July 1923. It resulted in a disappointing grade. He went back to Göttingen to become assistant of Max Born, who accepted him in spite of that. Well, Heisenberg had kind of failed in the experimental topics, but Born was wise enough to appreciate his other qualities. Heisenberg habilitated only a year later at the Georg August University. Well, the administrative boundaries 100 years ago were obviously different than today, and don't you university administrators wish that at least some of those conditions came back? The definitive paper of November 16, 1925 in Zeitschrift für Physik in volume 35 by Born, Heisenberg and Jordan is mentioned in the dedication text. And in the introduction of the papers, the authors state, I jumped to the English translation, this paper is an attempt to expand the general quantum mechanics theory, the foundations of which have been described into previous papers by the authors. And that is a reference to the preceding volumes 33 by Heisenberg and 34 by Born and Jordan. So that was kind of an Initialzündung blown by Heisenberg, and aren't we happy and lucky today that he did it with his colleagues in Göttingen? I think we are. Well, Göttingen, Copenhagen, and other places had a vibrant science environment with an enormous breadth and depth. And such an environment is obviously important for bright minds to solve nagging problems, for curious minds to explore the previously unthinkable, and for innovators to try to do things differently. So following that thought, one may ask the question, what was the spirit of Born's institute? And let me quote from Heisenberg's obituary to Max Born when he died in 1970. Born verbreitete in seinen Seminaren ganz systematisch die Überzeugung, dass es sich letzten Endes nicht darum handeln könnte, komplizierte Atom- oder Molekülmodelle nach der alten Mechanik durchzurechnen, sondern darum ging, eine neue Mechanik zu schaffen. In his seminars, Born created systematically the conviction that the goal cannot be to calculate complicated models of atoms or molecules, but that a new kind of mechanics had to be created. Well, that worked fine here. Physics and mathematics joined forces, and quantum mechanics was developed with breathtaking speed. It happened at several places in parallel, and with Göttingen always in a prominent position. Well, Heisenberg traveled a lot, and some time ago I was tempted to impress you with a graph of his trips, a map, possibly, hopefully, with Göttingen as a prominent node. And I asked some artificial intelligence for help, but it failed miserably. I got a map with only a few lines on it, and Göttingen was placed in the middle of the Indian Ocean. I complained, and the answer was, well, yes, that's a bad mistake. I'll make you another version. But it was equally bad. So you get only a few words instead of this map. Of course, Heisenberg felt forces acting on him in his movements. And external forces are, like today, career opportunities, and as they opened, for instance, in Leipzig, Berlin, Göttingen, Munich, and of course, political developments, this term has been mentioned, that we often call difficult. But that's a physicist's euphemism when we really mean disastrous. Internal forces came from features of his personality, and let me mention the keywords: his feeling for Heimat, duty, responsibility, a natural friendliness, and resilience. So one may understand that or why he stayed in Germany throughout most difficult times. But immediately after the war, Heisenberg was detained to the British Farm Hall lockup with Max von Laue, Otto Hahn, Walter Gerlach, Karl Friedrich von Weizsäcker, and others. They were kept in isolation for some time, but on January 1st, 1946, Werner wrote a letter from the village of Alswede in North Rhine-Westphalia to his wife Elisabeth in Urfeld in Bavaria. Wir dürfen jetzt völlig frei herumlaufen und beliebig Briefe schreiben. Ebenso kannst du mit der gewöhnlichen Post an mich schreiben. We are now allowed to walk around freely and may write letters as we wish. Likewise, you may write to me using ordinary mail. He also mentioned briefly that in the not too far future they might be released into some normal life, possibly in Göttingen. Well, 3 weeks later, his wife Elisabeth, still in Urfeld, answered to Werner, und allmählich fangen die Gedanken auch an, sich irgendwelche Bilder für die Zukunft zu machen. Göttingen würde mich am meisten freuen. Du weißt ja, dass ich schon immer eine Vorliebe für Göttingen hatte. And gradually my thoughts are starting to form some kind of picture for the future. I would be most excited about Göttingen. As you know, I've always had a fondness for Göttingen. And so it happened, and the Heisenbergs lived in Göttingen until 1958. He became a professor at the university and director of the newly born Max Planck Institute of Physics. He organized that institute in an, we would say, interdisciplinary profile. And having worked on cosmic rays myself, I'm still today very impressed about the book on cosmic rays that Heisenberg edited in 1953 based on seminar contributions in Göttingen. It was an enormous progress compared to the previous edition done in Berlin in 1943, but it's not widely known today. They reconnected to the rest of the world and understood the basic features of extensive air showers, for instance, at thousands of GeV, and incredible energy at that time. And famous astronomer Ludwig Biermann contributed a chapter on what we call today the cosmic particle accelerators. And when they didn't have facts, their physics intuition was simply awesome. Maybe this was an early instance of astroparticle physics, which got its proper name only 40 years later. So in a sense, Heisenberg turned to particle physics here in Göttingen, and we should also remember that he was the German representative in the foundation process of CERN. Well, the institute moved to Munich on September 1st in 1958 and took on the new name Max Planck Institute for Physics and Astrophysics with Heisenberg and Biermann as directors. What happened then, that may be the topic of my dear colleague Wolfgang Hollig in a minute. So let me congratulate Göttingen on the EPS distinction. Obviously, many things have been done the right way in this city and its institutions, although I'm sure that the ratio of inspiration to transpiration was unfavorable sometimes. But well, the result is, said with the enthusiasm of northern Germany, at least not bad. The number of Nobel laureates has been mentioned, 40, and 14 of them got the award while actually working here. So while we celebrate the thoughtful foundations of quantum mechanics today, we all know how immense the impact of those thoughts have become. So may the EPS distinction be a source of further inspiration, regardless on the amount of transpiration on the way. May the distinction attract natural intelligence to Göttingen, as it worked out 100 years ago in publica commoda for the benefit of all. Thank you very much.
Now, then let me introduce to you Professor Wolfgang Hollig, who was already mentioned. He studied physics in Würzburg and gained his doctorate there as well. His habilitation in theoretical physics was at the University of Hamburg, and from 1990 to 1993 he worked as a research assistant at the Max Planck Institute for Physics in Munich, before accepting a professorship for theoretical physics at the University of Karlsruhe. So I think that's where your path crossed, I think. In 2002, he returned to the MPE for Physics in Munich as director and headed it as managing director from 2006 until 2012. Professor Hollig.
So thank you very much for this kind introduction. Dear ladies and gentlemen, I want to change a little bit the style. Sorry for my voice, I have got obviously some cold today. And will present a few slides in order to make the relation between the Max Planck Institute and the site of Göttingen more illustrative. So this, immediately when the Kaiser Wilhelm Society was founded in 1911, it was proposed that an institute for physics should be founded, which should promote research in theory and experiment. And scientists should be free of teaching and any other duties, so that could do research. And the ideal candidate for this institute was Albert Einstein at the time. Einstein had accepted. So in 1970, the Kaiser Wilhelm Institute for Physics was founded. Funnily, there was no building for this institute, so the institute was practically the flat of the director. So this was Einstein at his home. Part of the institute's mission was to distribute money in order to support theoretical and experimental research at other institutions, in particular at universities. And one of these places, in theory, was Göttingen. It was in the decade, the upcoming decade, the group of Born with Heisenberg and Jordan as young postdocs that we had collected. And the support of quantum mechanics was one of the first contacts of the Max Planck, at that time Kaiser Wilhelm Institute, and Göttingen. So in 1933, Einstein emigrated to the US. This was a severe cut. The institute needed a new director, and they found Peter Debye, who came from Leipzig to be a director from 35 on until 40, and the institute got a new building. Now they had a building in Berlin-Dahlem, but unfortunately this was taken over by the Heereswaffenamt, so army ordnance, in order to push for uranium research. Debye left. Officially he was on leave, so he did not emigrate to the US, to Cornell, and Heisenberg followed up as a director after the institute in 1942 was given back to the Kaiser Wilhelm Gesellschaft. So Heisenberg was now the director. Formerly, he was a deputy director, since Debye was officially still a director. Anyway, the institute was terminated after the war by US and Soviet army because they did not like that Germany continued research in this direction. Anyway, after the war in 1946, the Allies allowed to re-establish the former Kaiser Wilhelm Institute at Göttingen. Heisenberg, Weizsäcker and others returned from internment in Farm Hall in the UK, and the institute was renamed as Max Planck Institute, officially in 1948. That was after the Max Planck Society has been founded as the successor of the Kaiser Wilhelm Society. The director was again Werner Heisenberg, and the building was in the Bunsenstraße in Göttingen. It was the building of the former Aerodynamische Versuchsanstalt. The institute accommodated experimental physics and theoretical physics. The head of theory was Carl Friedrich von Weizsäcker. And besides elementary particles, there was an upcoming interest, more and more interest in cosmic rays and cosmic plasma physics. What is important also is that the increasing number of visiting scientists and the increasing international visibility and recognition was very important for the image of the physics research in this field in Germany. And also the research of Weizsäcker and astrophysics on the development of the planetary system, cosmic gas dynamics, turbulence theory, was the trigger for the astrophysics and plasma physics in Germany. That's where the Max Planck Institute of Plasma Physics later in the 60s has come out. Weizsäcker, moreover, was concerned with philosophical aspects of quantum mechanics and questions of the foundation. Whereas Heisenberg concentrated mainly on the theory of elementary particles and on quantum field theory. And now I come to quantum field theory, because this was a decisive step from quantum mechanics to quantum field theory. It was necessary, because it was soon found that quantum mechanics is insufficient. It is not relativistic. It does not obey the theory of relativity. It does not allow to describe photons. Photons were known as particles of light. They have been manifested in experiments, scattering of electrons and positons, Compton scattering, but no way to describe it in quantum mechanics. So a first step in this direction to improve this was done by Dirac in 1928. He wrote down a relativistic equation, the Dirac equation, which had nice success, could predict the fine structure of the hydrogen spectrum and so on. But again, it was full of problems. And the problems had the same basis as always, namely relativity, the equivalence of mass and energy. This means that particles can be annihilated and they can be created whenever the energy is high enough. So particle number is not conserved, and this was not allowed in the original quantum mechanics. So one needs a concept where particles is not particle number, is flexible. And this concept was quantum field theory, where particles are considered as the quanta of fields, so like photons as the quanta of the electromagnetic field. So already in 1928, the people who founded quantum mechanics now founded also quantum field theory. It was a quantization of the electromagnetic field and the matter field, the electron field. And this unified the principles of quantum theory and relativity, allows to describe processes between photons and electrons, allowed to make higher order predictions, which were measured afterwards by the experiment for length shift and the anomalous magnetic moment, and Feynman contributed an intuitive picture in terms of the Feynman graphs. So this was a big success, but Also here, problems, problems, problems. There were infinities, mathematical infinities, not defined quantities. Practical solutions were obtained by a method called renormalization, but this was considered by theorists to be tricky and not trustable. So it was not clear if this concept has a chance. It was a situation around 1950. In the 1950s, however, the situation changed. There was the so-called golden age of quantum field theory, which allowed a rigorous mathematical formulation on a solid basis. And this was done with the quantum field theory at Göttingen. This was these guys, called by Pauli the Feldverein, the field club. Harry Lehmann, he was assistant from with Friedrich Hund in Jena. Szymanczyk, he was a student of Heisenberg. And Zimmermann, who came from Freiburg after his Ph.D., done in mathematics. These were young postdocs. These pictures give a different expression, a different impression though, but at that time they were short after their getting their doctoral degrees. And these guys, they succeeded to put quantum field theory on a solid mathematical basis and avoiding all kinds of infinities. So from that time on, quantum field theory was accepted in the theory community. So here I have a few slides for experts, skip them. You see here in these typical publications at that time that the language of publication was in German. Now it is in English, more or less. But not only these foundations of quantum field theory was important, but also important theorems, which were derived in a rigorous formulation from quantum field theory. The CBT theorem by Gerhard Lüders, who was at the Max Planck Institute, spin statistics theorem also by Lüders together with Bruno Tumino, and the Reh-Schnieder theorem by Helmut Reh and Siegfried Schnieder. Let me briefly flash what this means. Here is Gerhard Lüders, who was a group leader at the Max Planck Institute in Göttingen in the theory division. Later, from 1960 on, he became professor in theoretical physics at Göttingen University, but he remained to be an external scientific member of the Max Planck Institute. Now, the CBT theorem is one of the most fundamental symmetries of symmetry theorem of nature. It says that when a combined transformation of particle into antiparticle, left and right, so space reflection, and time reversal, ingoing and outgoing reverse, are physical processes that are equivalent. And this could be derived from quantum field theory in a rigorous mathematical way. The spin statistics theorem says that only one particle can occupy one quantum state when the particle has a half-integer spin, like the electron. Whereas for particles with integer spin, there is no such restrictions. So this has an enormous impact on the distribution of particles on the various states that are available. So this is the way of counting. Originally, this was postulated by Pauli in 1925 already, in order to explain the structure of atoms and get the periodic table of the elements. But this was a postulate, and now from quantum field theory, one could derive that this is just a consequence of the principles of quantum field theory by mathematical deduction. And this was done in 1958 in a common work by Lüders and Tumino. Then there was a break. So from 1958 on, the institute was in Munich, was relocated. It covered now two institutes, physics and astrophysics. Astrophysics has been upgraded from the former division on subdivision on astrophysics. And now elementary particles was only one branch in quantum field theory, and this was headed again under the directorship of Heisenberg. And here is in this period, 1961, where the institute was already in Munich, the Rey-Schwieder theorem was proven, which is difficult to explain. It is something, the analogon of entanglement in quantum field theory. Entanglement in quantum mechanics should be known, at least at some level, and similar thing happens in quantum field theory, which is has been proven in this famous paper here. Now, Rey was a scientist in the theory division of the institute in Munich, and in '71 he became professor in Göttingen as well. So there was really a fruitful interconnection between the Max Planck Institute and the University of Göttingen. Now then, the further development was that Heisenberg retired in 1970, and Zimmermann, who was the former postdoc in the 50s, became now a director at the Munich Institute, and he maintained the quantum field theory and its mathematical foundation. And later on, this was applied to the upcoming gauge theories and to the precision tests of the electroweak and the strong interactions and the establishment of the, finally, of the Standard Model. At the University of Göttingen, also the mathematical, axiomatic and algebraic quantum field theory was maintained. So it was continued by Hans-Jürgen Borchers, who became professor in 1966, Gerhard Hegerfeld in 1974, and Detlef Buchholz later on, after the kind of successor of Borchers in 1997. So 2 pillars of quantum field theory on a solid mathematical basis. And as a summary, one can say nowadays that quantum field theory has been recognized to be the appropriate basic tool for the microscopic description of the fundamental interactions. Practically, it is the undisputed theoretical basis of particle physics, which has been crowned by our Standard Model now. And the credit to the historical contributions of Göttingen, well, is given by the EPS Historic Site Award, for which I congratulate very much. Hearty congratulations for this. Thank you.
Thank you very much. We're looking forward to hearing you again after our keynote for tonight's evening. And we're very happy and glad that we could welcome Arne Schölmerich here on stage in Göttingen. He's the leading expert on the history of science when it comes to quantum mechanics. Professor Schölmerich is a historian of science. He had studied natural sciences and philosophy in Hamburg, Oxford, and Munich, and his diplomas in physics and philosophy, and a doctorate then in mathematical physics. Later he switched to the history of science, worked at the Deutsche Museum in Munich, and was a principal investigator at the research group on the history of quantum theory at the MPE for History of Science in Berlin, I guess. Right. Since 2010, Professor Schölmerich is a research associate at the Department of History at the Humboldt University in Berlin, and since 2002, in addition, extraordinary professorship for the history of science at the TU Berlin. Welcome, Professor Schölmerich, and the stage is yours.
Thanks a lot for this warm welcome, and I was told to be brief, so it's my greeting to all of you of all tiers of society and of science, etc. Standing here is really a great honor to me. It's the second time, actually. Last time it was only 50 years, and it was 18 physicists. It was the Göttinger 18 of the Göttingen Declaration, where I had the pleasure to speak. Yet today it's 100 years, and probably it's much more than 18 physicists which are involved. My talk may contain some physics, but I will also tell you why we have these two grand pianos here, and why this is the only true music for this event, so just listen. Here we are. Can a whole town be a site, a historic site of physics? The European Physical Society has honored the city of Göttingen by making it an EPS Historic Site. We just witnessed this. So this is done, so I better should ask, in what sense can a whole town be a historic site of physics? While in the text of the plaque, there's already a rich list of now famous names who all worked and lived in Göttingen, one might wonder whether Göttingen as an academic center has not all along been an academic village or a scientific town. However, discussing this would take much more time than I actually have. But just let me give you a glimpse of the Göttingen scientific townscape. This is the Ostviertel. You probably don't see much, but this is now a little bit more obvious to see. If you had walked down Wilhelm Weber Straße in 1920, yes, it was that Wilhelm Weber who invented the telegraph together with Carl Friedrich Gauss in 1833. It was then you would have passed Felix Klein's house at number 3. This is just 300 meters east of the auditorium building where the teaching took place. At number 21, where Runge's son-in-law, Richard Courant, was a regular visitor, and David Hilber's house is at number 29. The Runges, and after Karl Runge's death in 1927, the Courants, who took over the villa, as well as the Hilberts, had large gardens, which they used for leisure, but also in part for science. As Courant recalled after the war from his student days, when he, and I quote, happened to have a student room on the 5th floor from which I could look out of my window and see Hilbert in his garden. One could also go and visit Hilbert in his garden. He spent his whole time gardening, and in between gardening and little chores, he went to a long blackboard, maybe 20 feet long, covered so that it could also in the rain he could walk up and down, doing his mathematics, and in between digging some flower beds. All day one could observe him. And later they became near neighbors on Wilhelm-Weber-Straße. I will come back to the role of Hilbert's garden for physics in a minute. When Eugen Wigner became Hilbert's assistant in 1927, for example, he lodged in number 22 of Wilhelm-Weber-Straße, just opposite of the Courants, and so one could go on. 300 meters south of Wilhelm-Weber-Straße's Planckstraße. No, not Max Planck, but it is named after the legal scholar Gottlieb Frank, actually Max Planck's great uncle. If you had walked down Planckstraße in the following year, 1921, you would have passed number 15, where Hermann Minkowski lived until his untimely death in 1909, before arriving at Max Born's new Göttingen home, number 21, which became a place of intense physics and equally passionate music making in the following 12 years. In his autobiography, Max Planck characterizes his creative space in Göttingen as follows, and I quote, "One room became a combined study, drawing room, and music room. My father-in-law gave me his grand piano, an excellent Steinway, which together with my own Steinway were put into a corner of this room. Yet it was still far from being crowded and could easily hold my desk, my whole library, and all our drawing room furniture. There was also a big veranda, half covered, half open, with a staircase leading to the large park-like garden with its lovely old trees and big lawns." This was where Born talked physics with Pauli, Heisenberg, Jordan, and others, and played on the two grand pianos with Heisenberg, even Mozart and Beethoven piano concertos on occasions such as Heisenberg's birthday. I don't know whether they have actually also performed Gustav Holst, which composed this piece in 1916, possibly. This is why I guess here we have these two grand pianos. They are even better maps from the quantum exhibit in the Forum Wissen. So if you go there, you can scan through year by year where people lived and how they moved. For example, in 1925, with Werner Heisenberg, Maria Göppert, and Hertha Sponer living next door to each other and only minutes away from Born, Hilbert, and Frank. However, this was a very short constellation, especially for Heisenberg, since he was always on the move. What kind of scientific place was Göttingen 100 years ago? So Göttingen was special. Indeed, this becomes even more obvious if one compares it with other university towns. Just have a look at Oxford. While the much older, often medieval universities like Oxford University practice the unity of living and learning together in colleges, there was typically the clear distinction of gown and town. The spaces of learning and living of the students and scholars were strictly separated from the other surrounding world. In Oxford, for example, this was also marked by Magdalen Bridge, which defines the border between academic Oxford and the commercial and industrial areas known for its car makers, Morris then and BMW now, where the normal people lived. Or there's a new model of learning that was introduced by no other than a former president of the United States of America, John Thomas Jefferson. After his presidency, he promoted the idea of an academical village, which he founded in 1819 in form of the University of Virginia, mixing architecture of Greek and Roman temples with a layout of a village. Jefferson gave each academic unit a pavilion. The library was like the Roman Pantheon and the like. It's obviously an architecture of the American democracy that determined the university. This was the beginning of the campus university, which quickly grew to grand style, for example, at Berkeley. If one looks for other important creative spaces of physics, one might also mention grand institutes, like the Physikalisch-Technische Reichsanstalt in Berlin, or somewhat later, Niels Bohr's Copenhagen Institute. These places, however, were at the most loosely linked to universities. However, Göttingen was not, or not anymore, a college university, nor was it a campus university or dominated by one big scientific institute. Rather, it was a small science town and, especially in the 19th century, since the 19th century, characterized by a wonderful interpenetration, or shall I say, superposition of private and academic spaces, where research activity was created which did not reflect so much democratic ideals, but rather the conception of the Bildungsbürgertum, and even more so by the practiced meritocracy in the sciences, as it had been introduced with the advent of the research university. Göttingen is undoubtedly one of the central places where quantum physics developed. It was where quantum mechanics was first established in the collaboration of Max Born, Werner Heisenberg, Pascal Jordan, as we have heard repeatedly. And this is what brings us today to Göttingen, of course. However, if one tries to find a clear line of development in the field of quantum physics in Göttingen, the results appears rather eclectic. What can be found are mostly isolated and often unrecognized works. The first were probably by Walter Ritz on his combination principle for spectral lines, and by Max Abraham on black body radiation. Paul Ehrenfest also took an early interest in the quantum hypothesis, and he was instrumental in recognizing the inevitable discontinuity it introduced while spending much time in Göttingen. However, he was unable to gain a position here or even some influence. Further important work was done by Walter Nernst and Johannes Stark. Nernst developed his heat theorem while already preparing to leave for Berlin, and Stark, having taken the general idea of the Stark effect from Woldemar Vogt, made his discovery only after he has left Göttingen. Max Born had turned to Thomson's atomic model for his Göttingen habilitation and subsequently attended Albert Einstein's Salzburg lecture of 1909 that put forward the irreversibility quantum theory had introduced. Born thus developed an interest in atomic physics and the quantum question. He contributed to the emerging field of quantum research through his work with Rudolf Ladenburg on black body radiation, with Theodore von Karman in their papers on specific heats at the same time as Peter Debye, and with Richard Courant developing a theory of Oettwer's law of the surface tension of liquids as an application of quantum theory. To give just a few examples from the years before the war. Both Born, who left Göttingen first for Berlin and then Frankfurt, and Debye had concentrated during the war on questions of what consequences would follow from Bohr's atom if it were taken seriously. Born, who served as a soldier in the First World War, was still able to form a kind of outpost of the Göttingen physicists in military service with Alfred Landé, Erwin Madelung, and others who used Bohr's quantum theory for the constitution of matter. Meanwhile, in Göttingen, Peter Debye had tried to photograph Bohr's quantum atom by diffraction of X-rays with Paul Scherrer, however without success. And he also analyzed the Zeeman effect with quantum theory, quite in parallel with Arnold Sommerfeld. It now somehow became the Göttingen credo to regard the quantum as a key to atomic structure of matter after the war, when the failure of the Bohr atom became apparent. Quantum concepts opened a fruitful path to matrix mechanics, a path that would be paved not least by Max Born and James Franck, and when they became Göttingen professors in 1921. So this story told this way does not provide a satisfactory description of the advent of quantum theory, I guess you will agree. It neither provides a conclusive development, nor does it refer to the conditions or driving forces behind these developments. And one person which I consider central hasn't been mentioned at all, the mathematician David Hilbert. True, there are few publications of Hilbert that were directly cited by quantum physicists, but there are other perspectives to look at the quantum revolution than just the published paper trail. My thesis is, for today, that by putting David Hilbert at the center of the story will explain a lot about Göttingen's special role and the reasons for its success in becoming a center of quantum physics. Let's call it the Hilbert picture. It's about the understanding of physical theory building, about his research politics, about staff recruitment and the use of resources in general, and last but not least, his contributions to that Göttingen atmosphere or spirit, or how we would like to call it, that made this place a leading center of modern physics and mathematics in the 1920s, attracting flocks of young researchers from all over the world. Let me quickly characterize 5 elements of the Hilbert picture. He is famous for his axiomatic method, but few people realize that this underwent a crucial development, and here I brought 2 quotes to you. One from his private notebook sometime between 1905 and 1910, where he wrote, "I protest against the objections that physics were not developed enough to be axiomatized. Any science is at any time not only ripe enough but requires, with necessity, axiomatization understood in the correct sense." And in order to learn a bit more what does it mean to use mathematical axiomatic method in the correct sense, I have another quote from the Mathematische Annalen from a paper called Axiomatisches Denken, Axiomatic Thinking. "I believe," Hilbert says, "everything that can be object of scientific thought at all becomes object of the axiomatic method and hence of mathematics as soon as it is ripe of forming a theory. By progressing to deeper and deeper layers of axioms in the above described sense, we gain also deeper and deeper insight in the nature of scientific thought itself and realize the unity of our knowledge more and more. Under the sign of the axiomatic method, mathematics appears to be called upon having the leading role in science." So Hilbert understood his mathematics as a kind of heuristics to help physicists who are not clear about their foundations to go ahead. Another element is how Hilbert used his, I would say, personal resources, that is his assistants. You don't have to read all the names. You can just see on the left-hand side, this is Hilbert's mathematics assistants, and on the right-hand side, starting in 1912, he also had a physics assistant as well. So basically, they came from Arnold Sommerfeld, and they were visiting him in his garden and telling him about the newest advances in quantum theory, so that he was up to date, what's happening. And there you can make some arguments to see who's paid better at what time. There's a time that the physics assistant is even paid better than the mathematics assistant, etc. So you can really look at how he spent his resources. A third element is Hilbert's role in recruitment of new professors. So this is also kind of a graphics trying to see what's the dynamics of professorial positions, and now you see what happens. First of all, there's this quote from Hilbert's autobiographical sketch from 1932, where he said, "I have never taken any interest in administrative matters, full stop." But then he proceeds, "But when it came to important decisions, especially appointments, the creation of new positions and all the like, I always took an active part," and that's true. It was Hilbert who was crucial in getting the right people to the place. And here you can see this great dynamics that in 1921, almost all professorships in physics were renewed. And it was Hilbert, and I show you now in the fourth element, how Hilbert actually not only spent, sondern diverted money. There was a Wolfskehl fund, which got interest every year, and the Wolfskehl fund was a prize money to solve Fermat's conjecture. But nobody solved the conjecture, and so they accumulated the interest of this prize money, and this could be spent for mathematics. But what did Hilbert do? He basically invited all people around who were doing quantum physics at this time, from Max Planck to Sommerfeld to Nernst to Born to Debye, and even he used some of the money to, as you have seen, that the position of Debye was even created before there was a vacancy, and this was done by using money from the Fermat Fund, so that he wanted to have already in 1914 somebody who really can talk about quantum physics. And there are more aspects or more elements of what I call the Hilbert picture, very significantly, but I don't have the time to go into it, that they introduced a curriculum. They started teaching quantum physics, first with Debye and then with Born and Frank. Well, the Hilbert picture and the Göttingen spirit, is this a part of the Hilbert picture? At least he tried his best to create one. So from this autobiographical sketch again, he recalls when he very early first came to Göttingen, but it was by no means easy for my wife and me to immediately feel at home at Göttingen in the somewhat chilly atmosphere of Göttingen at the time. We were often looked at with a shake of the head when we ignored the strict differences in rank and socialized causally with Privatdozenten and even students. And also in conversations after lectures, on walks and bike rides, in the garden, at social gatherings, and generally at any opportunity that presented itself, such discussions were often continued with students and colleagues. So this academic village or town also had to be created first of all, and my understanding is that it's rather David Hilbert, not Felix Klein, who really helped create an atmosphere. However, there's a problem with this Göttingen spirit. I'm sorry, because as Christian Joas from the Niels Bohr archives told us yesterday very convincingly, that Bohr's Institute claims that there was the Copenhagen spirit, and this Copenhagen spirit brought about quantum mechanics. And in some fields, probably there's also Munich. Interestingly, for Munich, it has become custom to talk of the Sommerfeld School, which is also kind of their students, and they proceed in on the lines. So, what can we do? My impression is that this talk is not this talking about spirit or school is probably not specific enough to capture what is the underlying reason for success. And just as in, say, interim conclusion, I would say good science needs good and long-term infrastructures. This is what I try to demonstrate with Hilbert's investments and recruitments, etc. So it's a long-term thing. And this needs a collaboration of mathematics, experimental, as well as theoretical physics. Well, physicists know there's also a Heisenberg picture. Who was Heisenberg? Well, first of all, he was an exchange student on which Sommerfeld and Born decided that he should come to Göttingen to learn a bit, I don't know, mathematics, learn Born's style of doing physics. He was then the first Rockefeller Foundation fellow at Copenhagen, a postdoc, and now what I marked in red already shows the problem we get, into which we get. Well, from September 24 to October 25, he was in Copenhagen. He only returned for a short visit to Göttingen in July 1925. He handed over his Umdeutungspaper to Max Born, and then he disappeared again to Copenhagen. So, sorry, this is already the, okay, we are at this point. This already makes us think, is he a Copenhagener at all? Well, we can vote on that. I don't know how to determine this question. It's probably not an analytical solution. At least he was one of the Göttingen 18. What I mean is, if you see that he was always away, he was commuting, he was in Copenhagen, he came from Munich, he returned to Munich to do his Ph.D., and already in May 1926, so he again went as a lecturer and assistant to Bohr to Copenhagen, and in a sense one is wondering, why didn't he present his Umdeutung paper to Bohr, because he was in Copenhagen, and why did he come back and bring it to Bonn? There are good reasons for this, because I will show you in a moment that it's sometimes not so easly to work with Bohr. But here, when I put some shadow on the right-hand side, this is more or less the Göttingen contributions to the development of quantum mechanics, and you see that Heisenberg wasn't present when Born and Jordan wrote their first paper, where they mentioned that one should only use observable quantities. They handed in this paper exactly at the time when Heisenberg was on Helgoland. And so at least they had the same idea, and you can trace it back even more. Then Heisenberg was not there when Born and Jordan wrote their paper on quantum mechanics, and actually Max Born had to order him back to write the Freeman paper. Okay, so there are probably degrees of being a Göttinger, and which brings us to the next perspective, well, there's a postdoc perspective. Now the people start traveling around, looking for ideas, trying to combine things from various places. So probably Heisenberg, he was the first German Rockefeller Fellow, and you can get a much sharper picture of Heisenberg in the postdoc picture. So, but, well, first of all, forget all about glorious superstar stories about Heisenberg. He wrote to his parents in 1923, as long as I'm here in Göttingen, I must do what Born wishes, just as in Munich I had to do what Sommerfeld wished, and you can extend it, and in Copenhagen this, on the right-hand side, these two blue tiles, which come from this quantum history wall, explain, two examples where Bohr said, stop, Heisenberg had already calculated a very nice semi-classical result for the energy of hydrogen and so on, but Bohr didn't like half-integer quantum numbers, and he said stop, and so there's only a letter and no paper. And the other is on his Umdeutungspaper. He didn't wait until Bohr came back from vacation and just sent it to the publisher. And Bohr was very angry because you have first to show it to the director before you send anything to the publisher. Anyway, and when he wrote to Wolfgang Pauli and sent him his manuscript on this famous Umdeutung paper, he wrote, "I believe that my work contains real physics, at least in the critical, this is negative part, as I would like to either finish it or burn it in the last days of my stay here in Göttingen, but perhaps people who are more capable can make something reasonable out of it." This type, you see that we probably need a different picture of this superstar Heisenberg. I'm really exaggerating for the sake of the argument. And so Alexei Korzhevnikov has illustrated this element in a very nice way, and I quote, "It requires some effort psychologically to think about Heisenberg and Pauli as vulnerable and insecure students without permanent positions and funding. But once we make this effort of historical empathy, we are better able to understand and reinterpret some of their important moves, choices, and ideas for the radical reconceptualizations of quantum theory during the 1920s. A small side remark, so think hard whether you would like to get rid of the postdoc, give every doctoral student a permanent position, they don't have to travel to, there's no insecurity. There are backdrops, but so you see that this postdoc suffering period also applied to Pauli and Heisenberg. Let's change the perspective once more, the Born picture. Well, we already have heard that Born spent a lot of time in Göttingen. He was a student here with Hilbert Minkowski, Runge, and Vogt. He did his PhD. First, he tried to do with Klein. They didn't really work together well, so Runge took over. He did his habilitation at Göttingen, and he was for 5 years Privatdozent. Then he served in the war, and then after the war he went to Frankfurt, and there actually he turned to do experiments with molecular beams together with Stern, and in this context also the Stern-Gerlach experiment came up. When in 1920 he got the call now to return as a professor to Göttingen, he first of all insisted that Frank would be included in this package, and he turned out to be the key organizer of new institutes, of the curriculum and research fields. And in this sense, he very much extended already the quantum teaching Hilbert has started with Debye, for example. He did not need to wait until 1922 that Niels Bohr would come along and tell him that quantum theory is now the big thing. He already started earlier. And then he got Pauli from Sommerfeld in 1923, Heisenberg. Then he wrote this interesting paper on quantum mechanics, where there was no quantum mechanics yet, but he, in a sense, laid out a program. He saw the general direction, but he didn't know how to solve it yet. Then there was this big success of quantum mechanics, and after that, and Heisenberg already absent, he made a next big contribution, the statistical interpretation of the wave function. And Heisenberg came back as an interim professor because Born wanted to go to the US. And you know the rest of the story, that then Göttingen became a place where flocks of postdocs from the US and all over the world, the Oppenheimer, Weisskopf, Wigner, Stellers, etc., came, and in 1933, Bonn was subject to forced migration. When one goes further and looks and takes seriously Born's program to create a new quantum mechanics, then an interesting picture emerges, and it looks quite different. It's not so much a breakthrough picture, but 4 lines of development, or should I say 4 voices, if you like, which let appear the route to quantum mechanics as a quartet, sometimes harmonious, sometimes not. But in this picture, that you can properly identify that Born with Frank was interested in atomic and molecular beams, so they had experimental grounding. Born, for example, determined the mean free length of the silver atoms still in Frankfurt, but brought all his experimental apparatus to Göttingen. And still in 1925, Born had students working on molecular beams. Born was interested in many electron theory, first on the solid-state case with Emmerich-Brody, using perturbation theory, celestial mechanics. Later with Pauli and Heisenberg, he used this as kind of preparatory efforts to see where the old quantum theory would fail. Born was very much struck by the Ramsauer effect. When in 1920 Ramsauer first presented his effect, nobody cared because he's one of the Leonard School people. But in 1921, Frank wrote a paper by Ramsauer that I am not able to believe, though I cannot show any mistake in his experiment. And Born said, it's a simply crazy claim by Ramsauer. So he asked Hertha Sponer to do experiments on the Ramsauer effect, and Friedrich Hund tried a theory, first without quantum theory, which didn't lead to anything, and in the end, Born and Jordan tackled the problem of explaining the Ramsauer effect. And last but not least, clearly, Born was interested, and especially Frank, in collision processes. Quantum theory must also describe aperiodic phenomena, especially collisions. And here, where the difference calculus emerges, and just, I think it's already very long now, this talk, but this quote is nice. Born writes to Einstein, chiefly, however, I'm interested in the also quite mysterious difference calculus that is behind the quantum theory of atomic structure. With Jordan, I'm systematically examining, though with limited mental effort, every imaginable correspondence relationship between classical multiply periodic systems and quantum atoms. This is a preliminary work for an investigation into the processes of atomic collisions, quenching of fluorescence, synthesized fluorescence, a la Frank, etc. So my favorite view on the quantum revolution, if you will, is it's rather a co-working of different lines of attack. And so you know from mathematics that there is a parallelogram rule, that one force goes in one direction, one in the other, and they add up and go into a third direction. And in a sense, these 4 different forces push the Born group in a certain direction, which finally then brought about the famous papers and situation. I cannot stop without telling you that clearly one should combine this Born postdoc and also a gender picture. And by now we had yesterday afternoon a full session of women in the history of quantum mechanics in the Forum Wissen. So I just mention that at least we have now identified 6 women, postdocs, whatever, in Göttingen, so you only have to look a little bit harder and stop to talk about Knabenphysik. There's now publications coming out, Physikjournal has a little series about it. So Göttingen is a historic site indeed, but I won't say that there's a Göttingen school. It's rather not simply a Göttingen spirit. It's something like a scientific town where scientific and private spaces were in superposition, and which is most important, it had an organized, rich infrastructure of manifold resources, of people, of wise professors, sometimes even putting the money in different fields, and it was meant to, in collaborating, in going beyond a typical borders of status, etc. And so I think the research on what in particular is the Göttingen spirit, the special thing about Göttingen, can still go on. And as Christian Joas also in his keynote yesterday stressed, we haven't looked enough into how applications also contributed in the understanding of quantum theory and the formulation of further results. And with this, I will stop here and hope we have a nice buffet and some time to discuss in more detail. Thank you very much.
Damske, ganz herzlichen Dank. Members of the university choir, they performed what Gustav Holst had written in his, when he composed it as original thought. And Antonius, thank you very much for the idea to include that. Thank you for your participation. Thank you very much. Now, I'm only left with the last thing. Those of you who know how to get to the Alte Mensa, it's just across the place, the Wilhelmsplatz. And those of you who know, please take somebody who doesn't know and bring them over there. There is the reception, courtesy of the city and the University of Göttingen. Go over there, there's foods and drinks, and enjoy talking about everything you've learned and heard today. And enjoy still the ongoing physics conference. Good night.